Moving on from general flows, we're going to go into an isolated external flow in regard to drag and lift. So here it shows a Boeing 767 and the disruptions on the top of a cumulus cloud, and it clearly shows the counter-rotating trailing of the vortices. So you see these right here as it has extended through. Okay, and so here you can see you're going to have drag and lift, right? Because you can think of drag if you have this wing. So we'll look at it from here, like on an XY axis. If you have this kind of dimension as a wing, and you have some streamlines going over and under. And so for drag and lift, they're computed and looked at very differently, but on a surface level, like an XY plot, they look very similar. And so you will have this force here, and then because of that, you'll have these streamlines going the opposite direction, right? And so you will have both of those happening at the same time. So you can think of this as a stationary body with just drag happening over and under. And so you can experience, you can see the after effects of this disruption. And then you can have lift, which helps enable just exactly what it says, to help enable the plane to lift. And you can see the lift happening in the disruption as well. So you can see both of those things happening simultaneously. Here's the objectives. And so here, just again, I went way forward. Okay. Fluid flow, and we know that that can be the liquid or the gas, over solid bodies frequently occur in practice, and it is responsible for numerous physical phenomena such as the drag force acting on automobiles, power lines, trees, and underwater pipelines. The lift developed by airplane wings. Okay. Upward draft of rain, snow, hail, and dust particles in high winds. The transportation of red blood cells by blood flow. We've been looking at a little bit of anatomy in this class, not too much, but a little bit. The entrainment and disbursement of liquid droplets by sprays, the vibration and noise generated by bodies moving in a fluid, and the power generated by wind turbines. A fluid moving over a stationary body, such as the wind blowing over a building, and a body moving through a quiescent fluid, such as a car moving through the air, are referred to as flow over bodies or external flow. So when we are looking at the difference in definition from the drag force to the lift force, the drag force is going to happen parallel to the solid body, and the lift force is going to happen perpendicular. So let's look back at this airplane. So again, if we have this XY axis with these streamlines, right? And so we still have this force because we're cutting through, and thus our streamlines are going the opposite direction. Our lift, or our drag force is going to be happening parallel. You see, you have your force here, and thus your drag force will be happening parallel, okay? Depending on the way that the force is happening. Your lift force is happening perpendicular, right? So it's lifting the plane up, and the drag force is happening perpendicular to the wing. And so here, flow over bodies is commonly encountered in practice. You can see here again that you would have a force, and then your drag would be parallel to the force, and then your lift would be perpendicular. And here's some more examples here. So the flow fields and geometries for most external flow problems are too complicated, and we have to rely on correlations based on experimental data. It is very complicated when you're talking about the magnitudes of lift versus drag, particularly lift. That's very, very difficult. And so having these correlations based on experimental data is very helpful. You have the free stream velocity, the velocity of the fluid approaching a body. You have the two-dimensional flow, when the body is very long and of constant cross-section, and the flow is normal to the body, so you can think of like a pipe. Axisymmetric flow, when the body possesses a rotational symmetry about its axis in the flow direction. The flow in this case would also be two-dimensional. So you can think of the axisymmetric like the wing that I drew, right? You've got some symmetry. Three-dimensional flow over a body that cannot be modeled as two-dimension or axisymmetric, such as a flow over a car, right? Because I can't cut that in half or fold it, or there's no line of symmetry there. Incompressible flows over automobiles, submarines, buildings. Compressible flows over high-speed aircraft, rockets, missiles. Compressibility effects are negligible at low velocities. And so you can kind of see that the automobiles, those submarines, those buildings, those have that low velocities when compared to high-speed aircraft, rockets, missiles, things that reach Mach or above. Streamlined body, if the conscious effort is made to align its shape with the anticipated streamlines in the flow. Streamlined bodies such as race cars, airplanes appear to be contoured and sleek. And so, you can think of like our wing. That could be also considered as both a axisymmetric flow and then also a streamlined body. Bluff or blunt body, if a body such as a building tends to block the flow, usually it's much easier to force a streamlined body through a fluid, right? This is going to be very blunt. So here you can see long cylinder, two-dimensional, axisymmetric, and then three-dimensional flows. So this is two-dimensional. This would also be, it is thinner, but if it was very thick, that could also be a blunt body, right? Axisymmetric. You can take that symmetric. And so that would be the streamlined body. And then this car, which is 3D or three-dimensional, you can see that we would probably also classify this as a streamlined body when compared to a blunt building, right? But maybe this vehicle, in comparison to maybe a race car or, something like that, is probably less streamlined than that. But overall, we would take this as a streamlined body as well. So here it's much easier to force a streamlined body than a blunt body through a fluid, of course. So you can see here the difference. When you're comparing these two, you could classify this as blunt, and then this one is streamlined, because you're reducing the amount of effort that it takes to cut through, right? You're kind of stopped here, whereas this is more of a fluid flow. We talked about that when we talked about rounding pipes, that it's much easier on the fluid to go through something that's curved versus a sharp 90-degree angle, right? This would be more difficult. So it's much easier to force a streamlined body than a blunt body through a fluid. And so you can see that you need 70 horsepower to achieve the 60 mile an hour versus only 50 horsepower to achieve the 60 mile an hour. So it's just more efficient as well. So drag and lift. A body meets some resistance when it is forced to move through a fluid, especially a liquid. Right, we know that. A fluid may exert forces and moments on a body in and out of various directions. Drag is the force a flowing fluid exerts on a body in the flow direction, right? This is parallel. Drag force can be measured directly by simply attaching the body subjected to fluid flow to a calibrated spring and measuring the displacement in the flow direction, and that's because it's parallel. Drag is usually an undesirable effect, like friction, right? This can be equated to friction, not equated from a calculating standpoint, but from a symmetry standpoint. We do our best to minimize it, and that's where we get into streamlined bodies versus blunt bodies. In some cases, drag produces a very beneficial effect, and we try to minimize it, like on brakes. And here's high winds knocking down trees, power lines, and even people as a result of the drag force. So lift, the components of the pressure and wall shear forces in the direction normal to, whoop, my gosh. This is just not liking me today. Normal to, or perpendicular to the flow tend to move the body in that direction, and their sum is called lift. The fluid forces may generate moments and cause the body to rotate. So it can rotate. That's usually why you have two wings, right? Because if you just had, a plane, or let's just say a cylinder, right, with one wing, if you got lift on here, it would just continue to rotate. You just continue to rotate. Rolling moment, the moment about the flow direction. Yawing moment, the moment about the lift direction. And then pitching moment, the moment about the side force direction. And then here you see the formulas for drag force, lift force. So here is another depiction of that airplane wing. They're shaped and positioned to generate sufficient lift during flight while keeping drag at a minimum. So this is where we're wanting the lift, but we're trying to minimize the amount of drag, right? Because we know that that's going to require, like in the car, more horsepower. It's going to require more energy. It's going to require more fuel, things like that. Pressure above and below atmospheric pressure are indicated by pluses and minuses signs respectively. So A, you can see drag force acting on a flat plate parallel to the flow depends on wall shear only. And then for B, drag force acting on a flat plate normal to the flow depends on the pressure only and is independent of the wall shear, which acts normal to the free stream flow. So just a couple of schematics here. Drag and lift forces depend on the density of the fluid, right? Because it's not only the solid body and its geometric composition, but it depends on what it's cutting through, right? What that solid body is cutting through. So it depends on the density of the fluid, the upstream velocity, the size, the shape, orientation of the body, all of those things. It is more convenient to work with appropriate dimensionless numbers that represent the drag and lift characteristics of the body. And these numbers are called CD, which is the drag coefficient, and the CL, which is the lift coefficient. And you see that formula here, drag coefficient and lift coefficient. And you can see here that this is the A is the frontal area, and then here is the dynamic pressure. Okay, in lift and drag calculations of some thin bodies, such as airfoils, A is taken to be the planform area, which is the area seen by a person looking at the body from above, so from a topographical view or a bird's eye view. in the direction normal to the body. And that's, so you see, whoop, and that's for thin bodies. And that's because if you looked at it normal to, just on its side, it wouldn't, you wouldn't be calculating much because it would be so thin. So you look at it from a bird's eye view. Here during a free fall, a body reaches its terminal velocity when the drag force equals the weight of the body minus the buoyant force. And so you can see that. So friction and pressure drag. The drag force is the net force exerted by a fluid on a body in the direction of the flow due to the combined effects of the wall shear and pressure forces. Remember, it's parallel to. The part of the drag that is due directly to wall shear stress is called the skin friction drag, or just friction drag, either one, since it's caused by frictional effects. The part that is due directly to pressure is called pressure drag, or also form drag, because of its strong dependence on the form or the shape of the body. Okay, and so you see, you have that here, drag coefficient. There you go. Okay, and then the friction drag is the component of the wall shear force in the direction of the flow. So remember, when you see drag, you're going to get parallel, and thus it depends on the orientation of the body as well as the magnitude of the wall shear stress. For parallel flow over a flat surface, the drag coefficient is equal to the friction coefficient. Friction drag is a strong function of viscosity because you can think of those forces and those streamlines sticking, right? You can think of that liquid sticking to the body. So friction drag is a strong function of viscosity. Of course, you're going to get that friction, right? And increases with increasing viscosity. So that relation makes sense. Here you can see drag is due entirely to friction drag for a flat plate parallel to the flow. So you can see that here. And you can see it is due entirely to the pressure drag for a plate normal to the flow, and is due to both, but mostly pressure drag for a cylinder normal to the flow. The total drag coefficient, CD, is lowest for the parallel flat plate, highest for the vertical flat plate, and in between, but close to that of a vertical flat plate for a cylinder. So it's lowest for here. What is happening? Okay, lowest, and then highest, and almost highest. Right, and I would say middle, but here, but close to that of a vertical plate for a cylinder. So we talked about that we want to reduce that drag, right? We want to reduce it, and some of the ways that we do that is geometry. Streamlining decreases pressure drag by delaying boundary layer separation and thus reducing the pressure difference between the front and back of the body, but increases the friction drag by increasing the surface area, right? Because if you make something bigger, then you are going to have more surface area, more of that body to experience that friction drag. The end result depends on which effects dominate. Okay. So here, the variation of the drag coefficient of a long elliptical cylinder with aspect ratio. Here, CD is based on the frontal area, BD, where B is the width of the 2D body in the page. So here, the drag coefficient decreases drastically as the ellipse becomes slimmer, right? Because you've got less of it to experience that friction. The reduction in the drag coefficient at high aspect ratios is primarily due to the boundary layer staying attached to the surface longer and resulting in pressure recovery. Streamlining has the added benefit of reducing vibration and noise. Right? So this is an added bonus. Streamlining should be considered only for blunt bodies that are subjected to high velocity fluid flow, and thus high Reynolds numbers, for which flow separation is a real possibility. Streamline is not necessary for bodies that typically involve low Reynolds number flows. It's just not, it just doesn't pay off. So here, what is that flow separation that we just talked about? At sufficiently high velocities, the fluid stream detaches itself from the body of the fluid, the surface of the body. So here you see that separation point here. And again, you see the separation point, and then its reattachment point. So you see it's detaching and then reattaching here. And then flow separation over a backward facing step along a wall. Okay. So the separation region, when a fluid separates from a body, it forms a separate region between the body and the fluid stream. This is a low pressure region behind the body where recirculating and backflow occurs. So you can see that here, where it separates and you get that backflow. The larger the separated region, the larger the pressure drag. The effects of flow separation are felt far downstream in the form of reduced velocity, and that's in relation to the upstream velocity. And then wake, the region of flow trailing the body where the effects of the body on the velocity are felt. Viscous and rotational effects are the most significant in the boundary layer, the separated region, and the wake. And so you see everything here is that wake region. And you can kind of think of this as like a boat, because you always see that, the wake behind it. That's pretty normal. So here, this is at large angles of attack, usually larger than 15 degrees. Flow may separate completely from the top surface of an airfoil, reducing lift drastically and causing the airfoil to stall. An important consequence of flow separation is the formation and shedding of circulating fluid structures called vortices. We've seen those in the wake region. Periodic generation of these vortices downstream is recalled to vortex shedding. And then the vibrations generated by vortices near the body may cause the body to resonate to dangerous levels. So drag coefficients measured under typical operating conditions is used to characterize the drag behavior of the various natural and man-made bodies. Usually the total, which is friction plus pressure, drag coefficient is reported. So that's usually the outcome of what we look at when we're analyzing it. So here, again, it does other behaviors: low, which is creeping, moderate, which is laminar, and then high, which is turbulent regions of the Reynolds number. Inertia effects are negligible in low or creeping number flows, which is also called creeping flows. And the fluid wraps around the body really smoothly. And here's that formula for creeping flows. And then when we're talking about Stokes' law is often applicable to dust particles in the air and suspended solid particles in water. Here's just a little note: the drag coefficient for many, but not all geometries remain essentially constant at Reynolds numbers above 10 to the power of 4. So here you can see the sphere, a hemisphere, a circular disc, and then a circular disc that is parallel to the flow. And so you can see those two, normal to and parallel to the flow, and the drag coefficients. So drag coefficients of various two-dimensional bodies for Reynolds numbers greater than 10 to the 4, based on the frontal area in the direction normal to the page for the use of drag force relation. And then again, drag coefficients for various two-dimensional bodies for Reynolds numbers greater than 4. 10 to the 4, sorry about that. Again, more drag coefficients, but this is three-dimensional. And again, additional three-dimensional bodies based on the frontal area for Reynolds greater than 10 to the 4. Again, but now you get a person. So observations from the drag coefficient table. So what we just looked at, what you can observe is the orientation of the body relative to the direction of the flow has a major influence on the drag coefficient. So if you want to go back and look at those, you definitely can. Going to keep this kind of rolling so that we can get through this chapter. But the orientation, a major takeaway that you will find is the orientation of the body relative to the direction of the flow has a major influence on the drag coefficient. For blunt bodies with sharp corners, such as flow over a rectangular block or a flat plate normal to the flow, separation occurs at the edges of the front impact surfaces with no significant change in the character of flow. Therefore, the drag coefficient of such bodies is nearly independent of the Reynolds number. The drag coefficient of a long rectangular rod can be reduced almost by half from 2.2 to 1.2 by rounding the corners. So that's why you'll see that a lot in production, because it is reducing that drag coefficient. So we talked a little bit biological systems and drag. The concept of drag also has important consequences for biological systems. Bodies of fish, especially the ones that swim fast for long distances, dolphins, are highly streamlined. You can tell by the body. They are very streamlined animals to minimize drag. The drag coefficient of dolphin based on their wet skin is about 0.0035, comparable to that of a flat plate in turbulent flow. Airplanes, which look somewhat like big birds, that's not a coincidence, retract their wheels after takeoff in order to reduce drag and thus fuel consumption, right? Because we're wanting to reduce the drag, that friction that viscosity that we are experiencing. The flexible structure of plants enables them to reduce drag at high winds by changing their shape. And also, if those winds are high enough, it'll break. It'll have the material reach its failure point on that stress strain curve. Large flat leaves, for example, curl into low drag conical shape at high winds, while tree branches cluster to reduce drag. So they have natural abilities to protect themselves. Flexible trunks bend over under the influence of wind to reduce drag, and the bending moment is lowered by reducing the frontal area. Horse and bicycle riders lean forward as much as they can to reduce drag. So the goal is to reduce the drag, right? We want to become more efficient. Here you can see birds teach us a lesson by drag reduction, by extending their beak forward and folding their feet backwards during flight. Drag coefficient of vehicles, they're definitely, if you have looked over the history of vehicles, really, that they are becoming much more sleek. Particularly, I have noticed this in electric vehicles, where the whole goal of an electric vehicle is to become more efficient and to be able to get the most out of the electricity that you use. The drag coefficients of vehicles range from about 1 to large semi-trailers to 0.4 for minivans, 0.3 for passenger cars, 0.2 for race cars, and theoretical lower limits is about 0.1. In general, the more blunt the vehicle, the higher the drag coefficient. Of course, because it's less efficient. It's harder to go through that fluid. Installing a fairing reduces the drag coefficient of tractor trailing rigs by about 20% by making the frontal surface more streamlined. As a rule of thumb, the percentage of fuel savings due to reduced drag is about half the percent of a drag reduction at highway speeds. So it's huge. And then here you see that Toyota Prius has a drag coefficient of 0.26, one of the lowest for a passenger car, right? I mean, that's really close. I mean, it's still rounded up, closer to passenger cars, but I mean, no one's getting their groceries in a race car, right? No one's going to do that. So we know that this is, going to be unattainable for right now for just regular everyday vehicles. But to get 0.26 for passenger cars is remarkable. Here you can see those flows and those Reynolds numbers for each geometry of the vehicle. Streamlines around an aerodynamically designed modern car closely resembles the streamlines around a car in an ideal potential flow, assumes negligible friction, except near the rear end, resulting in a low drag coefficient. And you can see, of course, ideal when we talk about, you see the potential flows here. So when we talk about something ideal, we're negating friction, right? Ideal, we're not considering friction. And so you see these streamlines just come nicely off of here. But in real, you do have turbulence. The aerodynamic drag is negligible at low speeds. That's because it's easier for the air to detach, but becomes significant at speeds above 50 kilometers an hour. At highway speeds, a driver can often save fuel in hot weather by running the air conditioner instead of driving with the windows rolled down. That's interesting because I remember when the opposite was thought, oh, roll the windows down, so we don't have to use air conditioning. The turbulence and additional drag generated by open windows consumes more fuel than the air conditioner does. And this is also due to the progress that we've made just by way of air conditioning and more efficient air conditioning as well. The drag coefficient of bodies following other moving bodies closely can be reduced considerably due to drafting. And you can see this is because of the falling into that low pressure region, that circular region behind, that detached where you're breaking off of that streamline and you're reattaching and you get that backwards flow again. So following in here, you're being pulled with it, and it's just kind of helping you. This is something that you definitely don't want to do on the highway, especially because people, I don't think they do it much anymore, but some people do it behind semis, and that can end not well for you or anyone else. So definitely don't do that on the highway. Superposition, the shapes of many bodies encountered in practice are not simple, of course, but such bodies can be treated conventionally in drag force calculations by considering them to be composed of two or more simple bodies. Satellite dish mounted on a roof with a cylinder bar, for example, can be considered to be the combination of a hemispherical body and a cylinder. So, like when we draw, right? So of course that doesn't look exactly like a satellite dish, but when calculating, this is pretty good. Then the drag coefficient of the body can be determined approximately by using superposition. So here, when we're talking about parallel flow over flat plates, velocity boundary layer is the region of the flow above the plate bounded by this little S looking here, in which the effects of the viscous shearing forces caused by fluid viscosity are felt. The boundary layer thickness here is typically defined as the distance y from the surface at which u equals 0.99 v. And then the hypothetical curve of U equals 0.99V divides the flow into two regions. And those two regions are the boundary layer region. The viscous effects and the velocity changes are significant. And in the irrotational flow region, the frictional effects are negligible and the velocity remains essentially constant. So you can see, we've talked about this laminar boundary layer, and you can see these are really consistent, really uniform. The transition, it's when they start to get a little disrupted, and then you get into that turbulent boundary layer where they're just really chaotic here. And so you see you have this viscous sublayer down here at the bottom. The schematic is showing, while not to scale, the development of the boundary layer for flow over a flat plate in the different flow regimes. You see right here this viscous sublayer, that's the bottom. Right above that you've got the buffer layer, and then above that you've got the overlap layer. And for here you see this boundary layer thickness. And then here, critical point here where we are in our laminar boundary and right when we start transitioning into the transition region and thus going into the turbulent region. So when we talk about the turbulent boundary layer, we can reduce it down to 4 regions. And so you have, we just kind of went over these, that viscous sublayer, that buffer layer, that overlap layer, and then the turbulent layer. Let's go back to the schematic. So you see this viscous sublayer, it's closest to that plate, followed by that buffer layer, and then following that, the overlap layer, and then the rest of it is that turbulent layer up to where we, stop looking at it. And so here we have those friction coefficients on a flat plate. So you have here friction force on a flat plate, flow over a flat plate, all of these things just showing you what can be equal to 0. We will go through these when we work through them, of course. And just a note here, for a parallel flow over a flat plate, the pressure drag is 0. And thus the drag coefficient is equal to the friction coefficient, and the drag force is equal to the friction force. So you'll see that when we work it. And then here, just a reminder, I've seen it a little bit, that this is, it's just delta. There's a lot of deltas. There's, that's delta, and then one that's kind of like that's delta. And so just remember that this is the difference. That's all it's looking at when we're looking here. The development of a boundary layer on a surface is due to the no-slip condition and friction. So here when we're talking about when we transition, right, you have that transition period. When you transition from that laminar to turbulent flow, depends on the surface geometry, surface roughness, upstream velocity, surface tension, surface temperature, and the type of fluid. All of those things and others decides when we are going to go and move out from that laminar flow into that turbulent flow and when we are going to experience that transition period. It's best characterized by that Reynolds number, right? And the Reynolds number at a distance x from the leading edge of the flat plate is expressed as this, where v is the upstream velocity and x is the characteristic length of the geometry because, of course, it's dependent on the surface geometry. For a flat plate, it is the length of the plate in the flow direction. So depending on how that plate is angled or, the direction in which it's laying normal to, that's what you would look at it in relation to the flow direction. So here for a flow over a smooth, flat plate, transition from laminar to turbulent begins at the Reynolds number equal to 1 times 10 to the 5th, but does not become fully turbulent before the Reynolds number reaches much higher values, typically around 3 times 10 to the 6th. in engineering analysis, a good accepted value for the critical Reynolds number, so remember Reynolds critical, is this. And you see that in regard to X. Actual value of the engineering critical Reynolds number for a flat plate may vary somewhere between these, depending on the surface roughness, turbulence levels, variation of pressure along the surface. It's highly, highly dependent on not only the body that you're looking at, but the fluid that you are cutting through and the environmental effects. It's dependent on all of it. You have a frictional coefficient. The friction coefficient for laminar flow over a plate can be determined theoretically by solving the conservation of mass and momentum equations numerically. So here for turbulent flow, it must be determined experimentally and expressed by empirical correlations and those relationships that we talked about earlier. The variation of the local friction coefficient for flow over a plate. Note that the vertical scale of the boundary layer is greatly exaggerated in this sketch, so don't take that into account when you're looking at it. Right? Sometimes we exaggerate things to convey a message. Here's these formulas here, these laminar changes, right? Turbulent changes, things like that. Average friction coefficient over the entire plate. So you have laminar coefficient of friction, turbulent coefficient of friction. Here you have these being solved and reducing down. When laminar flow region is not disregarded, you can use here, so we'll talk about these, of course, in another video. The average friction coefficient over a surface is determined by integrating the local friction coefficient over the entire surface. The values shown here are for a laminar flat plate boundary layer. Okay. For laminar flow, the friction coefficient depends only on the Reynolds number, and the surface roughness has no effect. But for turbulent flow, surface roughness causes that friction coefficient to increase several-fold. So it's for lack of better words, a profound effect, to the point that in the fully rough turbulent regimen, the friction coefficient is a function of surface roughness alone and is independent of the Reynolds number. And here's that fully rough turbulent regimen. Here you see that this little e is the surface roughness, L is the length of the plate in the flow direction, and then you can use that relation for turbulent flow on rough surfaces for Reynolds numbers in excess of 10 to the 6, especially when surface roughness, the ratio of surface roughness to length of the plate is greater than 10 to the 4. CF increases several-fold with roughness in turbulent flow. We talked about that. It's independent of the Reynolds number in the fully rough region, right? That has that profound effect, that surface roughness has a profound effect. The chart is the flat plate analog of the Moody chart for pipe flows. So when we're talking about flow over cylinders and spheres, it's frequently encountered in practice. The tubes, and flow over cylinders and spheres, it says it's frequently encountered in practice. All of these shapes, all of these geometries are frequently encountered in practice, especially when we can reduce those complex geometries down to, what was our example, our satellite dish, right? Also looks like a grill. So when you can reduce them down to geometries, you definitely can. But cylinders and spheres are also frequently encountered in practice because of that streamlined body effect, right? It's much less of a blunt force than something like a square or a rectangle, but from a manufacturing standpoint, it's much more costly to produce a cylinder or a sphere versus just cut a piece of material into a square or a rectangle, right? But however, the payoff can be very great when you start getting into those streamline geometries. The tubes in a shell and tube heat exchanger involve both internal flow through the tubes and external flow around the tubes. So remember for this shell and tube heat exchanger, and remember what a heat exchanger is. It's meant to exchange heat either directly or indirectly with a material. And so here you could have, so let's say this is a hot liquid, right? A liquid that is hot, or, oops, did my subscripts backwards. We have a liquid that is hot and a liquid that is cold, but maybe we can't have them mix, right? And so we have an internal flow and an external flow, but we need them to not mix together. Many sports, such as soccer, tennis, and golf, involve flow over spherical balls, right? The characteristic length of a circular cylinder or sphere is taken to be the external diameter. Thus, the Reynolds number is defined as R equals VD over V, where V is the uniform velocity of the fluid as it approaches the cylinder or sphere. The critical Reynolds numbers for a flow across the circular cylinder or sphere is about, here's this critical region here, that is the boundary layer remains laminar for this, is transitional for this, and then you can see fully turbulent here. So you can see this is that transitional period. Right? And here is that laminar. And this is turbulent. And this, in particular, is when it starts to get to that Reynolds critical, right? But less than this, you're going to have that laminar flow. So here, you have a laminar boundary layer separation with a turbulent wake, flow over a circular cylinder. This could be, doesn't matter what it is, could be a golf ball, could be a tennis ball, but you see how you have this just very beautiful flow over here. That laminar flow, you have lots of turbulence. You have those wakes here behind it, and just that turbulent chaos here. Flow in the wake region is characterized by periodic vortex formation and low pressures, and you can see that. For flow over cylinder or sphere, both the friction drag and pressure drag can be significant. The high pressure in the vicinity of the stagnation point, where there's no movement, and the low pressure on the opposite side in the wake produce a net force on the body in the direction of the flow. The drag force is primarily due to friction drag at low Reynolds numbers, less than 10, and to pressure drag at high Reynolds numbers in excess of 5,000. Both effects are significant at intermediate Reynolds numbers. And so here you can see the smooth cylinders, average drag coefficient for cross flow over a smooth cylinder in a smooth sphere. And so you see smooth cylinder and smooth sphere. These are some of the observations from those curves. For Reynolds numbers less than 1, we have the creeping flow, right? Low, slow. The drag coefficient decreases with increasing Reynolds numbers. For a sphere, this is it. There's no flow separation in this regimen. So you think if you have this ball, right? Or for flow separation, I find it's easier to maybe look at like a stair. So normally for flow separation, you'd have something here. I mean, it can go all the way out to here, right? Or it can go to here. Either way, it just separates from this line right here. So when you start talking about no flow separation, Well, that's because it's moving really slow. If you have something that's just moving really slow, well, then it's just going to keep moving really slow. You're just not even going to separate. It's just going to creep on by. Right? Think of like a snail. It just creeps on by. For Reynolds, in equal to 10, separation starts occurring at the rear of the body with a vortex shedding starting about 90. The region of separation increases with increasing Reynolds number up to about 10 to the third. At this point, the drag is mostly about 95% due to pressure drag. The drag coefficient continues to decrease with increasing numbers in this range. In the moderate range, the drag coefficient remains relatively constant, so not a huge amount of change here. We've kind of plateaued. This behavior is characteristic of bluff bodies. The flow in the boundary layer is laminar in this range, but the flow in the separated region past the cylinder or sphere is highly turbulent with a wake turbulent, wide wake turbulent, right? So if you have something like this and you have some beautiful laminar flow, oh my gosh, that's looking so good, and then just chaos behind here. Wide turbulent wake. There's a sudden drop in the drag coefficient somewhere in the range of right here, usually around 2 times 10 to the 5th. This large reduction in CD is due to the flow in the boundary layer becoming turbulent. So that sudden drop is because of the turbulence, which moves the separation point further on the rear of the body, reducing the size of the wake and thus the magnitude of the pressure drop. This is in contrast to streamlined bodies, which experience an increase in drag coefficient, mostly due to that friction when the boundary layer becomes turbulent. And then, of course, we do have a transitional regime for this period right here, in which CD dips to a minimum value and then slowly rises to its final turbulent value here. Here's more formulas as well. And then you can see in A and B. So A, the flow visualization of a smooth sphere at a Reynolds number 15,000. And then B is a sphere at Reynolds 30,000 with a tripwire. The delay of the boundary layer separation is clearly seen by comparing the two photographs. Let's leave it here and pick up with a second lecture.